You may remember when Sasha was kicking off the overall event this morning, he mentioned that one of our panelists was missing. That's a panelist that was from Duke Energy, Travis Bronson, who's a lead AI specialist there with Duke. He got called in for storm duty, which we all realize is a part of working in the utility industry. So we just want to say that we're going to take a little opportunity to try and get a little more audience participation in the sections where we're going to have Travis talking about the utilities perspective here. We also want to just say thank you to all the utility folks and crews that are down still working in Western North Carolina, and the crews that'll inevitably be restoring power as Milton bears down on Florida. So our topic is visual inspection, which has been around the utility industry probably since the day the first poles and wires were erected. Over the past several years, I would say we've seen a lot more virtualization of it, meaning that we're collecting image data, video data, and the inspector may not be out in the field. The inspector might be sitting at a workstation evaluating this information. And even more recently, we see an interest in grabbing onto computer vision, this field of artificial intelligence where we can have a computer interpret what we see in the images. We know that kind of can sometimes make people nervous, like we're gonna train a model to do what, and especially coming from like the actual inspectors that have done this historically in the field, that might create some level of mistrust, or they might be uneasy or anxious about this concept. So today we wanted to bring together a few people who are actually doing this kind of thing, and at the same time get some perspective from utility folks that are online and in the room here as we go through a discussion, and hopefully through that we can sort of ease the anxiety. What we're going to do first is have the panelists sort of introduce themselves. We'll go with John first, and then Neela and Robert.
Hi, my name is John Eddins. I have been in the utility sector since about 2006. Started a company, had a good time with that, had some success, and very recently we were acquired by another company, Sam Company, really focused on driving the inspection automation market as best we can for our utility customers.
Hey everyone, I'm Neela Vengateshwaran. I'm a data scientist within the pre-sales analytics team at SAS. So I joined SAS as an intern when I was doing my master's here at the NC State, and it's been 8 years with SAS now. My role is mostly working with customers and helping them solve their analytical AI use cases using our most recent cloud-native SAS Via technology. I focus mostly on the computer vision, deep learning side of things, and also enabling customers to help them integrate SAS Via with their existing open source workloads.
Hey everyone, my name is Robert Blanchard. I'm on the same team with Neela. I'm a data scientist. I focus on deep learning, computer vision. Joined SAS and I went to the education division with Carlos, who presented earlier on the time series forecasting. And then Carlos came over to the global technology practice. I joined him over here, and it's great to be with you today.
So originally when we were planning this out, and Travis was going to be with us, we were going to be focused mostly on kind of the routine or annual type inspections. We're going to take a slight detour, and we're going to talk a little bit about using this kind of an approach when you're talking about preparedness and assessment of natural disaster. So John, I'm going to ask you first to comment a little bit about what you've been observing, especially over the past few weeks here. It's top of mind as these couple of hurricanes have hit the southeast.
Yeah, so it's been wild, honestly. There's been some real strong storms that, Helene was catastrophic for Western North Carolina, did a lot of damage down Florida and basically up Georgia coming its way up. But it's been interesting through the damage assessment process, seeing the way that, you bring in thousands and thousands of people, each of these various utilities that are all trying to do this damage assessment, capturing data through drones, dash cams, cell phones, whatever the mechanisms may be. And then you're trying to aggregate this data and then prioritize, associating the damage with your GIS. So you could be like, all right, these structures are down, here's what we need to fix this. How do we share this information? How do we get it out to the appropriate teams so they can properly equip themselves for the restoration efforts? It's crazy, for lack of better phrasing, just how chaotic these storm environments can really be. And, ultimately, the damage assessment piece of that is the first piece of the puzzle. Like, you've got to know what issues you've got where, and how is it that we should best go about replacing or fixing the components that have been damaged, to get millions of people's lives started back in some normal fashion. Electricity is the heartbeat of most people's lives for the most part. So it's been fascinating to see, just how, crazy this Helene specifically has been to the grid and the impact that it's had. But, ultimately, the way that digital technologies like the ones that we're talking about now, getting all this drone data to a field of folks that are, sitting behind computers and can do, dynamic assessments, and then, prioritization of the restoration efforts, repairs. That's where you really get to see technology, the rubber meeting the road, like doing a lot for, each of us outside of kind of a blue sky application. When you've got these dark sky, events, it's cool to see how the technology can really help push things along.
So this is an area where we were going to get some input from Travis and some perspective from the utility side. I'm curious, anyone in the room here or maybe online, whether you work for a utility or maybe you're consulting and supporting utility, have you seen the use of this kind of, or want to share some perspective on the use of this type of data, either for preparedness and like preparing for, or in the assessment stages?
Craig, I'll maybe jump in. I can really see how, especially the topic we're talking about today, computer vision, could really speed up the detection of issues in these kinds of situations. So if a drone or a helicopter flies over a disaster area, you pump that data into CartoVid, and then, John, you brought this up the other day. You actually said, can we get a model to identify where assets are? In like a 2-3 hour video. You don't want to sit there for 2-3 hours, even if you have it sped up. But we could, switch that out for some kind of a defect or disaster, or broken pole, or even something that hasn't caused a problem yet, but the storm has maybe pushed a tree such that it's going to be a problem. So you haven't detected it perhaps on the grid, but it will be a problem later on. So identifying that quickly, I think this technology can really lend itself to speeding that up. Perhaps.
Yeah, absolutely. All right, so let's bridge and talk more holistically, not just the damage assessment part, but the more routine kind of annualized inspection perspective as well. And I'm curious, like, for the utility folks that are here or in the room or online, are you already capturing image and video data to support inspection processes? Show of hands, image and video data. Yeah. Is it?
Don't work at a utility, the consultant, and we do have drones that we use in our inspection process.
Okay.
Bring that data back, link it to mapping data points, and
yeah. So we're seeing drones more prevalently. How about dash cams? We're hearing more and more about the use of dash cam imagery and video. Any of the utility folks or consulting folks seeing that in support of inspection? Online, anybody?
No, we've had some people trained on operating the
Oh,
drones.
all right. I say that because I heard a talk with NIPA, and they actually trained their linemen for, transmission, right? So when they're doing inspection, they might be able to do the inspection fully with a drone. So it was, yeah. Well, there's more drones out there, but they found it to be the better approach. So even though it got adopted pretty well for linemen who aren't used to flying drones.
So we have a customer I can reveal, a utility company, which uses drones heavily, to look at some of the transmitters or the lines, the poles, and things like that. My question is to you, Robert. One of the things which I'm very curious to know is things like embedded intelligence, right? The time it takes to take a picture, right? Hopefully it is the right picture, right? And that goes into something which Sasha said, how are these drone pilots trained to take the picture? Then how quickly can you analyze and saying there is once again, use the word anomaly, right? With any of the lines and things like that. That's what I would be curious to know.
That's a great question. It really comes down to, do you already have a model trained yet? Training a model is very time intensive, and I know we'll probably get into some of those details around that. But if you already have a trained model, then the inference time is actually extremely fast. You'll see here today, we're going to talk about some of what we're doing to improve performance. But we're actually using several models. These models are something of a mixture of experts. They work together to divide and conquer the computer vision problem. And we deploy these models using SAS technology, SAS event stream processing. And these are 3 computer vision models, each with 1 million or more parameters. And we're able to inference or score, make predictions on 5 frames per second. I think roughly thereabouts, with a single GPU, which is pretty darn good, given that there are 3 computer vision models working together. But in terms of the training time, that is more difficult and more time consuming. We have developed a series of pipelines to incorporate and make that process more automated and streamlined. And the pipeline includes like automated computer vision and so forth. We actually have a slide on. Do we have the clicker?
Yeah, we do. You want to jump there now, or you want to?
No, we'll come back to it, but we'll definitely show you what these pipelines look like for just model development.
If I may say so. Typically speaking, right, we'll have the opportunity to work with you guys so that that solution becomes part of our company, right? Something which Eddie, whom I work with, has touched upon is that if you go with the solutions which are already there, right, then the IP of that rests with that company, right? They're saying this is our so-called, if I may use the word, cookie cutter solution, right? And this is what you can use, right? Versus, the SaaS platform where what I'm trying to get is what would be the difference between going to a company which says that I have an expertise versus coming to the SaaS. And going back to Carlos, he basically proved, right, in his last demo that, the SaaS model was doing better, right? That is where my thought process are, right, in trying to partner with SaaS. Yeah, a lot of questions.
That's an excellent point. I mean, I would almost, and I'm going to pivot over to my co-panelists here for this as well. But I would almost say that the proof is in the pudding. You've got to see the predictions on video that the models have never seen. We're actually going to show you that today as well. Proof is in the pudding there. And then if you think about model development, quality of a model, it is model and data. Trash in, trash out. So data is another important and key component that we'll touch on later. I'm kind of jumping around.
That's fine. I think it's a good set of questions. And I think part of what the messaging that's going to come across here is we're partnering together with other companies. And SAS that is very good at the computer vision and the analytics piece, but there's a lot of aspects and challenges with the collection of the data, the management of the data, and the preparation and labeling of data so that you can even use it to generate models. So I'm going to kind of redirect to John, because John and his company have been working for for a few years, several years, in the direction of trying to provide a better platform for doing those upfront pieces of the work. And then we're going to evolve the discussion more directly at what you were just asking about. So, John, you want to take just a minute here? And I think
Yeah, sure.
I'll control the.
Yeah. So push the green button.
Yeah.
All right. So to piggyback on what Craig was saying there, when we first developed the platform, the intent of the platform was to ingest and amalgamate as much data as we possibly could. And then we had our own data science team that, we had aspirations of building models, building plugins for those models to be implemented. COVID hit, and our data science team, to the point that Kimberly made earlier, they were wooed by, some much bigger players, and good for them. But that caused us to sit there and, we're a small company, like, oh man, we've got to pivot. What do? We can't stay competitive in this specific space. So what we could do is we've got terabytes and terabytes of data, and we do a really good job of organizing that data. And, we have a good platform for labeling that data. What we don't have is the data scientists to actually make, we're the grocery store. We've got the ingredients, but we don't have the chefs. So that's really kind of the collaboration with SAS for us in many respects, is they've got excellent chefs. We've got all this data. We've got the means and mechanisms of, during a storm event, having, thousands of entities, pushing data to an environment that can be consumed and, leveraged by the utilities for damage assessment and, dark sky event, blue sky event. It's real easy to drive a car down the road and capture miles and miles of distribution data very cheaply, very efficiently, versus, drones are great, a little more expensive to capture a mile of drone data. But, to the hole in the market that we, when we had to pivot, it was, all right, how can we change our platform to, corral the data, have it indexed if it's, not stored in our system, have it, properly, cultivated and curated, and generate derivatives from it if it is in our system. And then, we got various, I'm not even sure what all you guys are seeing right now, but I guess I should look. Sorry. But once we've got that data, to your question earlier, the first piece of the puzzle is, for any AI, is having, labeled data or data to be fed into the models to train. So that, for the utility space, is a bit of a gap. EPRI's got a lot of data. There are entities out there. The utilities themselves have a lot of data, but it is difficult for the data sciences teams. I know with some of our large customers that we have, just getting access to that information. Someone may have a hard drive full of drone data sitting on their desk, and no one has any clue that that's there. And then, there's just so much segmentation and fragmentation of access to the data that, that's a big accomplishment in and of itself, having kind of a system of record that you can, hey, we're going to go here. If it's not here, we can assume it doesn't exist. And that works out well for the digital inspectors who can go in and evaluate information. And through that evaluation process, they're ultimately building these training data sets that can then be leveraged by the data science team to build better, stronger models. And then, you've got access to all this data, which, again, another complication in the life cycle of this AI development is, having a good testing ground to apply, your trained models against. And then you're getting some level of comfort on the accuracy, or, is this model performing like we want it to? And, then taking the next step. All right, well, yes, it is. Let's make it accessible to folks, the business units, or no, let's go back to the drawing board, put in, refine the training data, do whatever it is that needs to be done to, let the chefs, end up with this beautiful cake or whatever the output is, you know.
Cool. All right, thanks. So now we're going to try and, oh, question, go ahead.
We've seen, and so I just wanted to comment on a couple that I've seen, and not around damage assessment per se, but definitely computer vision related. And the first would be at my time at Duke Energy, there was they had a vegetation management program where they'd fly over with LiDAR and take that. Part one was capturing the data and seeing where the vegetation. Then part two is let's do an estimate of how the tree is going to grow in the next year to predict where you need to trim, which had pretty successful results. And then at my current role, I'm with National Grid up in Boston. And one of the things they're doing at piloting is network video recorders in a substation that can identify the person in the fence, right, and create an alarm or a message that indicates that they've discovered that they've recognized a human being or whatever.
Yeah.
On site.
Excellent. We're actually doing some related work in computer vision related to worker safety. Most of those use cases right now have been focused more in manufacturing environments, like inside warehouse, distribution centers, and that sort of thing. But definitely some overlap when you look at an individual getting into an area where it's an unsafe environment for them to be in, and creating an alert or warning quickly about that. So definitely applicable, I think, across most, if not all, industrial areas where we have people working in close proximity to equipment. But turning back to the story about starting to apply AI and how can AI help. So Robert, can you back up just a little, start at a high level and sort of describe the overall approach when it comes to first, identifying equipment that we're interested in, but then beyond that, well, classifying the equipment and maybe classifying defects on the equipment. So you can just at a high level first, and then we'll start diving in deeper.
Sure, definitely. And so I have to laugh at Shadi's comment earlier. He said he was a geek and a nerd and he didn't have a jacket on. We are definitely some of the geekiest, nerdiest people you'll see, and we have jackets on. So I think his model was overfit. I'm going to go a little geeky and a little nerdy. We use several computer vision models. The first is a YOLO style model where we identify the equipment location. Now, if you're familiar with computer vision, every computer vision model, you have to resize that image. We cannot train a model on an image that's 5,000 by 3,000 pixels. Not today, at least. The hardware doesn't exist for that, to put a billion or 100 million parameter model in, and you've got these really large images that have to come in, and you're analyzing 30 or 100 of them at a time. Just can't be done. So we resize the image down to a smaller size. Well, when you do that, you lose important information. If we're looking for a broken shell on an insulator, especially if the distance from the drone is relatively far, that's going to be hard to capture when we take that high resolution image and we bring it to a low resolution. So the first stage model is just a YOLO, and we tell the YOLO, find all the important assets. We don't care what it is, just find the assets. And so the YOLO model goes in and it finds all the equipment, and it passes that to a next stage model, which is the general classifier. And the general classifier looks at the extractions. I'm going to pause here. I missed a step. We take those predictions from the YOLO and we map it back to high resolution. We want to extract the highest resolution because remember, we're looking for defects that you would maybe not see when you resize to a smaller resolution. So go back to the higher resolution, we crop those out, and we pass those to a general classifier who breaks the problem down into even a sub-problem. We say, oh, here are insulators, here are transformers, here are cross arms. Now go to your model specialist, and we pass the insulators to the insulator defect model and the transformer to the transformer defect model, cross arm to the cross arm defect model. And then that model, which is specialized in detecting defects, detects whether it's defective or not. And we combine this all into one image frame that you see as we inference across a video. So I think I went a little deeper than you wanted me to.
That's okay. But maybe, Neela, you could expand a little bit more on how open source is involved in the process.
Sure. As John was talking about, how important data labeling is before we move into the modeling stage, right? So that is one of the main areas where we use open source, because when we compare any traditional model, before model building, data labeling is important. So in computer vision, it's a little different in how we do the data labeling. to explain the use case that Robert was talking about, what we do for the labeling is we just go in, look at the image, and simply draw bounding boxes, like rectangular boxes around those entities of interest, so that we have the coordinates of where these entities are before we pass them into a model. So that's one of the areas where we use open source tools and frameworks right now. And after meeting John, like, we see this as a potential area where we could collaborate, where we get the data labeled from the Car2It platform, and then use SAS analytics to build the models and do the inferencing there. Another interesting thing that we observed in talking with customers lately is customers themselves have a team of data scientists which are building their own open source computer vision models. So we want to be able to ingest those models and bring them into the SAS ecosystem so that these can be deployed at the edge or in real time in stream. So this is made possible because these open source models could be exported into an industry standard format. We call this the Open Neural Network Exchange format. So once the model is packaged into that particular bundle, it can easily be brought into the SAS ecosystem from which it can be deployed and inferenced easily.
Excellent. John, I'm not sure if there was anything else you wanted to add. Neela was just talking about labeling, as far as labeling and not just, you know, tagging an image to say it's this type of image or it contains this, but the bounding boxes and being able to describe what's inside the bounding box, especially if it's something defective.
Yeah. So, I mean, again, that's, you know, when people are going out and capturing this data, it isn't because it's riveting to watch a dash cam video of, you know, electrical circuitry. The reality is you're looking for issues that may compromise the grid or something. You've got a target. So anything that you may have a target for, you know, you've got a team that can sit there and evaluate, you know, via the platform, the imagery, label it, and then ultimately feed that labeled data into a model. And if you take, you know, utilities for the most part are all basically trying to accomplish the same goals. I mean, people have the same challenges. You know, storm specifically, everybody's, you know, kumbaya trying to help one another out to get the grid back up. You know, you will never see a more collaborative environment than a disaster recovery event for the utility sector. But in blue skies, same problems. You know, you got vegetative threats, you've got, you know, wildfire threats, you've got, you know, cracked insulators, broken cross arms, whatever the case may be. You know, to building out the digital inspection, you know, really process, taking the various labeled images and data sets and trying to amalgamate them to feed them into some, you know, grand unified theory or some, you know, some model that's got really broad applications for the utility sector. It makes a ton of sense. You know, we're all kind of in the same boat here, you know, trying to get to the other side of the shore ultimately. So how it is everyone can kind of work together, you know, get these labeled data sets, take various models, make them better. You know, it makes a ton of sense for the industry as a whole.
Yeah. Okay, thank you. So, Robert, could you share a little bit more perspective on like creating some form of structured workflow that gives a more guided approach to the model creation process?
Sure. So here on the screen, you see an example of these point and click tools that Neela and I have developed. And we've made these tools so that data scientists, you don't have to have a large team of data scientists, but you can just have one that's able to build sophisticated computer vision models. These tools are a brain dump of Neela, myself, and a few others. Everything we know and have learned about computer vision over the lifespan of learning and researching in this field. So it includes automated model development. So we look at different like model architectures and hyperparameters. Remember, quality of a model, it is the model and it's the data. So we test a whole bunch of different models against the data. We do this in a really sophisticated manner using, Carlos and Manib had alluded to it earlier, it's a genetic algorithm called Eagles that we leverage there. So that's the modeling front, but we also include data pieces that Neela's developed on her side.
Right. And I think the nice thing with using these tools is how we are able to collaborate because Robert is a SAS guy. Like, I don't know SAS much. Like, I use most of open source like Python. So if you've seen here, a lot of these nodes that we've developed integrate both SAS and Python code together. But the nice thing is it abstracts all of those complex details behind the scenes so that a user who's using this tool for the first time would just have to drag and drop and use these tools. So they don't have to know any of the coding behind the scenes. So it's easy for a team of data scientists who have like expertise in different skill sets be able to collaborate much more easily.
And you can schedule these, and we're in a collaboration with John to create and bring the modeling to his platform. I mean, he has an amazing platform for labeling images, which is a very tedious process, and not only labeling images but sorting through the data. He makes that first piece really convenient, and we're bringing the second piece hopefully into his platform for the modeling. And you're going to see like pipelines. These will be behind the scenes. You interact with his platform, but behind the scenes, these are scheduled and kicked off in a series to use that multi-stage computer vision model approach. We also have some generative data that we'll talk about here in a bit.
Yeah. Well, I would chime in. I'd carry that like a little bit further, but Robert brings up a really good point there. And you've got ultimately a wide range of end users for a product like this. You've got highly skilled technical data scientists that really understand the nuts and bolts of, what it is AI and machine vision is ultimately doing. Then you've got, folks that are highly skilled in other areas, but may not have any idea what AI ML even stands for. So, how is it that you can make something that's applicable to, the highly technical team and then the person that just wants to click a couple of buttons and end up with a result? And I think that, in conversations we've had kind of, with the SaaS platform, that seems to be like the direction you guys are going, which is really cool. You kind of have the capabilities for the folks that are highly technical to fine tune, take apart the, get behind the curtain and really, dig in. And then you've got, the easy button. So it's nice to see that that's kind of the, one, attainable, but two, the direction that we're kind of heading there, because it makes the tool applicable to the larger universe, in the electric ecosystem.
Yeah, sure. Neela, could you talk a little bit about the sort of trade-offs that come when you're weighing, the accuracy of a model versus the compute time you want to take?
That's a difficult question to answer because I think one challenge that we've been talking about is data labeling, but definitely another biggest challenge when it comes to computer vision is the compute time of running and training these computer vision models. Because this is the reason, because we have lots of data and also the quality of the data, because we are dealing with high resolution imagery. So we are talking in terms of like 5,000 by 3,000 pixels that Robert was talking about. And this is just one image. And when we have to train like thousands of images of this particular resolution, it's going to take way more time than what it would take for traditional machine learning models to train. So we, as data scientists, we definitely feel that we wouldn't want to compromise on the accuracy side of things, because compute is definitely expensive. But if we were to compromise on accuracy, the model isn't going to perform well. And so it cannot go into the deployment stage at all. So that is one thing that we often have discussions about with customers when trying to weigh in both aspects. And if we were to talk from our past experiences, like as we talk right now, I think there's one localizer model that Robert and I are running, and it's been running over the past 72 hours. And it's doing, I think, a few hundred evaluations over like hundreds of models. So it's a really time-consuming process and something that we want to weigh in when trying to talk about the time versus the cost.
Yeah, that's good. Thinking about trade-offs when you're in the training process. But there's also trade-offs when you go to execute a known good model and say, I want to run this cracked insulator defect model, and actually the several stages across, like you talked about, to identify where do we have insulators, and then the defect classifiers, and you want to select, say 40 miles worth of distribution, and you're going to set this job off to run. So could you talk a little bit more about when you get to executing the inferencing part?
Sure. It's actually, surprisingly, we've made it really easy. It's actually traditionally been the hardest part, I would say, of computer vision is to deploy, especially for real-time inferencing. But I'm going to click the slide. The video is very short. I didn't have access to your data, so I don't have a utility video. I had to buy this one off of a stock website, and it's like 10 seconds. But let's take a look at it. Oh, there's part of it. I'm going backwards. Let's see. I'll try to replay it several times. So I'm going to start the video, and I did superimpose some defective insulators on there because none of these were defective. But this is the model in play, and it's using SAS event stream processing. So we're getting, I think, about 5 frames per second for this model, and it's already over. So let's see if we can play again. I want to point out something, and we're going to talk about this in a bit, lessons learned. If you notice on the video, those insulators, the model's deeming those to be a single insulator. Lesson learned. This is data this model has never seen. To the gentleman's question earlier, how do you know your model's good enough? Proof is in the pudding. I see on LinkedIn, a lot of people will post computer vision videos detecting stuff, and boy, it looks great. And I think you trained on that data. You trained on that data, you're inferencing on that data, and you're showing us that. This is data the model has never seen before. So it's nice to see that given that it's never seen that, it's actually doing pretty well. And our inference rate is 5 frames per second with 3 models. That's really darn good. So it makes it easy.
Yeah. Oh, question, sure.
There you go.
So, this is very interesting because I've looked at something very similar with wind turbines. And what I was interested in is that you said you have different defect types. So how are you dealing with the defect, like the class imbalances that you wind up with? Because you're going to have some that, is your most common, and then you have your least common. So I was curious how you're doing that, if you are using the S word, the synthetic data, or how you're dealing with that.
Well, Neela, do you want to kick us off?
Sure. So I think similar to traditional machine learning model, we also do augmentation here. So we try to have more variance in the data. Mm-hmm. So especially for defective versus non-defective, we'll have like much lesser images on the defective type. So what we try to do is do different sorts of what we call as image mutations, which would be things like trying to vertically flip the data, horizontally flip the data, make rotations, like play with your brightness, the color of the image, the brightness, make it darker, lighter, so that the class imbalance is kind of negated in that. Also, while we do model development, and I think Robert can talk to it as well, we also make sure that we add a weighted variable so that it makes sure that the defective are not as less as compared to what the non-defective would be. So the weighted variable also comes into play when we try to put in the parameter values within the model.
Nice.
And I'll jump into some of the synthetic data. Mm-hmm. Sorry, I'm going to stand up just so I don't know why, it's easier to see up there than it is down there. We got a little picture here. This is a real image. It comes from EPRI. You have free use to use EPRI data, and it's labeled. So we don't have enough data to train a good model. So we've had to generate synthetic data. And here are some permutations. You'll notice we just take a random background from an open data set that we can use from the web. We apply a UNet to the entity of interest to extract out the entity, and then we superimpose it somewhere on the background. Now, when we superimpose it on the background, we do these augmentations that Neela was describing. We flip it, we change the color shading a bit, we'll resize it. So here, I'm just gonna walk through a few permutations. It's very random. Does anybody see the miss? The model made a mistake in this image. Does anybody see it? Yep, it's the building right there in the middle. Here's another one where no, this actually did pretty well. And then here's one where the model made a mistake. Do you see the mistake? Yeah, the costume. Yeah, it kind of fooled the model. But given that the model is being exposed to these very difficult permutations, it makes it more robust and more generalizable. And this really helps our modeling process. The other day we met, John, Neela, myself, Craig, and I think Sasha was there, and we were looking at images of the synthetic data and the model's predictions. And here's an example image where the model actually did really bad. And in that conversation, we realized we need to add more aggressive shading, bringing the entities darker, because you could have instances, this is EPRI, this is real data, you could have instances where it's fairly dark. So we've done that, improved the predictions. These are the predictions of the model. So this is holdout data. The model isn't trained on this. This is where the model is predicting. So including shading, these are some previous lessons learned, including shading. We ensure that the asset varies at a reasonable proportion to the background frame. So some of the open data sets that we were using, the background images were like 1,000 pixels by 700 pixels. But that's not representative of a drone image. A drone image, the width is 1.7 times the height. So when you have an insulator on a drone image and you resize that to a square, the entities of interest, they change in a way that when you superimpose on a square and resize it to a square, you don't have that same compression. So that was a lesson learned. So we've added that in. Ensure the background frame size represents the image frame's deployment state. Oh yeah, that's actually what I was. Oh, so that earlier bullet, that was an early mistake we made. Some of our background images were like 5,000 by 3,000. We would just resize the entity and throw it into the image. Well, some of our entities, because they were from EPRI and maybe the equipment was way far away, when we superimposed it, it became really small. So when we take this 5,000 by 3,000, we resize it, it disappears. And now we've got this label there that really doesn't have anything that exists. So,
Question.
oh, question.
I was a line inspector. So we did about 3,000 miles of lines, transmission lines of varying types. Now you're showing one use case. I mean, we're looking for things like a broken conductor, a strand of conductor, where the sun you had to get with the sun at the right angle, loose nuts, loose bolts. And we used to do lines two ways. Once with just a little Piper Cub, you'd fly the lines, so kind of like a drone, but you'd barf when you did the loop-to-loop. And then we'd go out with snowmobiles or trikes and just really slowly go. I'm just trying to understand. There was two guys, we did about 4,000 miles a year. And again, we would do it. So what's the cost benefit here? Why is this better?
Copy and paste. Copy and paste. It's cheap. Once this gets built and our pipelines are there, we can, so this is for one asset for two types of defect. I think we're looking at flash and broken shells, but we've got the pipelines, copy and paste next asset.
And I understand
Copy and paste next
you
asset.
still have to, we were two guys and two snowmobiles that would go look at this every year. Every year you have to fly a drone. You got to keep doing it, right? Maybe you could do it more often, because I think that's one of the benefits. But I'm just trying to understand, how do you get the other use cases, the ones where you have to position yourself? Like you said, resolution's a big issue, right? You have to be in the right location if it's a cloudy day. I mean, just things the eye can't catch. Maybe the resolution on the drone is better, maybe better sensors, right? I think that's kind of.
Well, rule of thumb, if a human can't see it, maybe the computer, you can't expect the computer vision model to see it. So the human has to be able to, even zooming in, if you can zoom in and say, okay, that's a problem, then we would expect the model to be able to do it. But if you can't do it, we don't expect the model to do it.
And the cost of the drone, so we're talking going through a remote, where I come from up north. I mean, we had 1,000 miles of DC line. I mean, we're talking nothing there. I mean, how's that? Okay.
Well, I actually think that John's come up with a really neat idea with the dash cam, and I know you can't drive throughout all terrain to look at the utility, but for some of your lines, you perhaps can use dash cam.
Yeah, I mean, dash cam, obviously, it's very, very cheap to drive a mile.
The swamps of Manitoba. Sure.
Well, but that's a good point, though. I mean, not all distribution circuitry is next to a road. So, but even if you've got, let's say 80%, which is probably reasonable, maybe a little low, that's a lot. You're able to more effectively and efficiently capture a lot of data that you can then apply models to quickly evaluate the data for something that you can take your field crews and be like, hey, we're not sure about this, or we definitely seem to have issues here. But I would also argue that, there's more to a utility than just a lineman. that's a critical piece of it. But one of our large customers, they fly their transmission circuitry, the 32,000 miles of transmission, they fly twice a year. Recently, they had the environmental team, there's something going on with bald eagles and having issues with transmission, high voltage transmission, where they're like, all right, we've got to identify every bald eagle's nest within some proximity to our high voltage line. Well, the transmission, the asset team and the vegetation team, pooled their money. They've got very expensive, gimbal systems in this case on the helicopters, and they've gone and captured this data. It's available for the enterprise. So, the environmental team knew that this data existed, and they're like, hey, you know what? Instead of doing another flight or having ground troops or doing X, Y, Z, we're going to have our people just get access to this data. And they knocked out this project, I think, within about 2 weeks, which is pretty fast. And in that process, they've actually generated data that could be leveraged or fed into a model that, hey, we've got to look for bald eagles or some other type of, large, distinct bird nesting pattern, and presuming that we've got enough data to feed into a model that you could get accurate results. But that's an effective use of the software beyond just the line. And you take that for distribution. You've got vegetative threats. You've got all types of different things outside of just the circuitry that if you can make that data accessible or apply models to, similar to what LiDAR does now in many cases, show us the problems we're going to have, and then you focus on that. If you can take that, remove some of the expensive LiDAR and apply it to, something as generic as a dash cam video, to where should we effectively look at or route our limited resources? It kind of makes a lot of sense.
So I want to thank all the panelists. We're a few minutes past our time slot already. I know there's more to talk about. I think we'll have to cover that at the social, or maybe if you're at the Drive Shack this evening, might be a good time to continue on with some discussion around computer vision. Thank you all.
Thank you.